If you've got a situation of two ramps, both of them 60 centimeters long, and these are the familiar ramps that we use in lab. Flip this, don't have the distraction. Okay, so we got two ramps, one here, one here. Roll balls down the ramps. We assume we have uniform acceleration on both ramps. They're both straight. The balls are reasonably smooth. The ramps are reasonably smooth. They're tracks. So they keep the ball in the track and so forth. So we ignore any little deviation from uniform acceleration. It'd be very minor in this case. So first piece of information I gave you, I timed it in my head, 1001, 1002, a little over 3 seconds. I'm saying 3.2 seconds. So it takes the first ball 60 centimeters from rest, 3.2 seconds. Okay. Travels 60 centimeters from rest in 3.2 seconds. And that's the end of the ramp. Then we do a simultaneous release the balls on both ramps. And we find the ball in the first ramp is 16 centimeters from the low end, and the second ball reached its end. Okay. Now there are a lot of questions I could ask. I chose to ask this: how fast was each ball traveling at this time? This time being when both balls reach the end. Then I made a comment. Just gave people a couple minutes to organize your thoughts, think, ask how many people have a strategy. Well, y'all just completed the first assignment on uniformly accelerated motion. And we've done a lot with it, with the rotating beam and all that stuff. Still, the whole picture is a fairly challenging situation. And I said that if you start from this question, you're going to have an awful hard time figuring out what to do. Okay, I would ignore this question. You understand it's a reasonable question. That's good. You understand that, yeah, maybe we can put things together and come up with an answer. Okay, but what I recommend you do when you see a problem that's fairly complex, it's going to have several steps, is you start by figuring out whatever you can figure out from whatever information you have, starting at the beginning. So I would focus on the question, what can you determine from this first bit of information? Okay, everybody, fairly quickly did the right thing here. There are a couple of ways to figure out this motion. Okay, first of all, you could say "60 centimeters over 3.2 seconds, 18.8 centimeters per second." Initial velocity 0, acceleration uniform, probably off the fourth. Maybe not. Yeah. Make sure we got the whole thing. Okay. Initial velocity 0, acceleration uniform implies some more stuff. Okay. So we haven't totally solved this motion. All we've got at this point is the average velocity. We don't have to follow this. We could use any of the equations of motion if we know the distance, the time, and the initial velocity. Okay. You can determine all kinds of stuff. I was recording. And I'm glad you didn't make me try to block you because you would steamroll me. Okay, we can immediately dive into the information here and determine the average velocity. Okay, and from that we can reason out other things. Okay, and or we could just go to the equations of motion. We've got three quantities here, right? Okay, we can solve the motion on the first ramp, and we know everything about the motion on the first ramp. So don't have any white chalk. Okay, I'll use it. There's white chalk. Okay, that's fine. So for this motion, find the acceleration. Okay, actually, we don't know V naught. No V naught. Displacement x minus x naught in t. We can find A and V. A, V, and T. Those are 5 quantities that we can use to characterize uniformly accelerated motion. Now, in reasoning these things out, we might well use the average velocity because in this case, the initial velocity is 0 and we're assuming uniform acceleration. And that's kind of a quick and dirty way to do it, but you can use the equations and either way is okay. So what we know now I say now we know everything about motion on ramp 1. Particularly, we know the equation of motion. We know x minus x naught equals v naught t plus 1/2 at squared, but of course, v naught is 0, so I just draw this little arrow saying that that's 0. Now that's what I mean. You know, when I ask some of you for a synopsis of what you got, if you're to the point where you can give me a synopsis, I would suggest when you get this, you write out v naught equals x minus x naught equals t equals a equals v equals, okay? So you write out and of course, you know V naught, you know x minus x naught, 60 centimeters, not 60. If you write the units and do the wrong calculation, the units will tell you that you did the wrong calculation. If you calculate a velocity and it should be an acceleration, and you call it an acceleration, if it's got units of velocity because you did the units, then all of a sudden there's a red flag and say, oh my, that was a bonehead mistake, let's fix that, okay? The real bonehead mistake is you don't write units. Write the doggone units. Do the dimensional analysis. You avoid bokus of errors, especially when you're new to a situation, okay? So make sure you do that. Okay, then we have t is 3.2 seconds, and then you have to fill in A and B, and then you can write this equation for the motion on the first ramp. Once you have the equation for the motion on the first ramp, what can you use it to find? Okay, knowing everything about the motion on ramp 1, particularly being able to fill in the quantities here, the quantities that you either know, well, x minus x naught is going to be different because it's like at time t. Okay, this is for any time t, right? between t equals 0 and 3.2 seconds, because after that it goes off the end of the ramp. There's your equation of motion. What is it that you know? You've calculated the acceleration. Now t is no longer 3.2 seconds. This is an equation of motion. And to make really explicit that this is the equation of motion, I'm going to want to write x of t equals x minus x naught, x of t minus x naught. Let me get it right. X of t minus x naught equals 1/2 at squared. Between 0 and 3.2 seconds. Okay. So there's a function of t. We could graph it. It's a simple parabola with its vertex at the origin of the t-axis. X this way, t this way. Okay. So we could even do this. The acceleration is the acceleration you calculated up here. Now, question is, you can answer, when is the ball 16 centimeters from the low end?
74 seconds.
You got to get out of that habit. It's a real pain, turned out yesterday.